This is one of a series of lectures produced by the Further Mathematics Support Programme for A-Level Maths Revision. In this lecture we're looking at the Edexcel Decision Maths 2 specification, and the topic is use of the Simplex algorithm. The specification simply says that you should be able to use the Simplex algorithm and Tableau for maximizing problems. It says you should really understand the meaning and be able to use slack variables. Now, in a linear programming problem, so far you have met constraints which are written in the form of an inequality. For example, we might have something like x plus 2y plus 5z is less than or equal to 23. Slack variables allow that to be written as an equality. So if we introduce a slack variable r, we get the following. Say that x plus 2y plus 5z plus r is equal to 23. And it's these which are written into the Simplex Tableau. So this table has been produced with that first equation in the top line, so that if we read along we can see that the x, y and z, the coefficients are 1, 2 and 5 in the first row, and the coefficient for r is 1. Now the basic variables, those are the values which currently have got some value. X, y and z are set at 0 to start off with, and the other values r, s and t, known as the basic values, have got some the basic variables have got some value. In this case r is equal to 23. The final line of the Tableau gives the objective function. This can be read off as p minus x minus 3y minus z is equal to 0. So at the current value we've got that the objective function p is equal to x plus 3z plus 3y, beg your pardon, plus z. Currently that's at 0. So with x, y and z all equal to 0, as they are, then the current objective is equal to 0. If you think about working with a graphical solution for linear programming problems, what happens is you start at the origin as indicated on the diagram, and then you can move round each of the vertices of the feasible region in turn until you find the maximum. Now what the Simplex algorithm does, it does this for you automatically, deciding first of all which point to move to first, and indeed how far to move. Now when we've got more than two variables, of course it's rather more difficult to draw a graph. We'd have a three-dimensional graph, but if we have 4, 5, then that would be totally impossible. So the algorithm, if you can imagine that the algorithm is doing the same thing as moving round a graph, but it's trying each vertex in turn. The first thing to decide is which of the variables x, y and z is going to be the best one to increase first of all. Now what we normally do is we say, well, let's take the most negative one, in this particular case y, and that means in effect we're moving up the y-axis. What we need to now decide is, well, how far do we move? Again, if you look at the graph, the intersection points with each of these lines, there are 3 of them here, but we only want to move to the first one. We don't want to move any further than that, because that would take us outside the feasible region. Now this is what's happening when, using the Simplex algorithm, we calculate what are called the theta values. These are the current value divided by the element which is in this column that we've just indicated. This is called the pivot column. So for the theta value for the first row, we would take the value 23 and divide that by 2, which gives us 11.5 obviously. You would do a similar thing for the other rows in the tableau, so for the basic variables s and t. So for example, let's say that we'd calculated the values of theta and they turn out to be negative and 12. Now that means that these are the values these are the distance we would have to move around our hypothetical graph that we've got. And what we want to do is to take the smallest positive value. Again, the reason for that is if we take a value which is larger than that, we would move outside the feasible region. Negative values would indicate that we're actually going in the wrong direction. So we want the smallest positive value of theta. In this case, it's the 11.5, and that indicates what's called the pivot row. And then that gives us this element here as the pivot. The next stage is now to change the values in the pivot column so that they have 1 at the pivot and all the other elements are zeros. The other thing that happens at this stage is that the basic variables change. We say that r is exiting. In fact, what's happening is that r becomes 0 and y enters the basic variables. So the basic variables are now y, s and t. Thinking about our graph again, what's happened is that the basic variables that they had are s and t. Those are the non-zero ones. This is at our origin, where in fact the zeros were x, y and z equal to 0. We've now moved up in the y direction, so that now y has got some value, so it's become a basic variable along with s and t, but at this constraint we've got r is equal to 0. So each of the lines represent one of the things x, y, z, r, s and t equal to 0. Actually these are planes if we're in 3 dimensions, so there's another axis which I've not indicated, just simply to try and keep my graph a little bit clearer. There's a sort of z-axis going in here, and what we've done is we've then moved to an intersection of different planes in the graph, but it's equivalent to what you did in Decision Maths 1 with your 2-dimensional graph with x and y. Sorry, that should have said x on that axis, the lower axis. Well, to make the value of the pivot equal to 1, we simply divide the pivot row by 2. So in other words, we're using the 2 that we calculated the theta value with and the value is now 11.2 for y. So we've moved up the y-axis, if you like, to a point 11.2. The other values in the rows are done by a series of what are called row operations, and hopefully that will become very clear when I go through an exam question in a minute. You don't really need the idea of a graph. You don't need to be able to reproduce that in an exam, but I think it helps to understand how the Simplex Tableau connects with the work that you did in D1. This exam question was from June 2010. So just reading through it. It says the tableau is the initial tableau for a linear programming problem in X, Y and Z. The objective is to maximize the profit P. So here we have the tableau with its basic variables marked R, S, T, and the variables X, Y, Z, R, S and T along the top. It says write down the profit equation represented by the initial tableau. So remember that the profit equation is in here. And so what we need to write down is that P minus X minus 2Y minus 6Z is equal to 0. So reading off the coefficients of X, Y and Z from the tableau, and the value at the end. We're asked then to take the most negative number in the profit row to indicate the pivot column at each stage, and to solve the linear programming problem. We should make the method clear by stating the row operations you use. And then finally, having done the tableau, state the final value of the objective function and of each variable. So going through this, and the top tableau there is the one that's just been on in the question. So we start off with the most negative value, which is -6. This is the pivot column, and calculate the theta values for each row. So the first one is 24 divided by 2 is 12. The next one, 28 divided by 4, which is 7. And 22 divided by 3, which is 7 1/3. The smallest value there is 7. So that gives us a pivot at this element here, which is in row S, column Z. So S is the exiting variable and Z the entering basic variable. So now moving down to the second tableau, we can write that in immediately then, that our basic variables are now R, Z, T. We want to make the pivot column equal to zeros and a 1 at the pivot. So the pivot itself becomes 1, and the other elements in that column are going to become zeros. To make the pivot equal to 1, we're going to divide this row here for S by 4. Now to do that, what we tend to do is to label these rows. So we call them R1, R2, R3 and R4. So these are the row operations that are referred to at the end of the table here. So for the pivot row R2, we're simply going to do R2 divided by 4. And that gives us a row which is equal to 1/2, 1/4, 1, 0, 1/4 and 0. And then a value 28 divided by 4 is 7. So that value 7 is the theta value that we had in the table above. Now the notation is that this now produces a new row 2. The reason for this is that Simplex tableaus are normally completed by computers, and what's happening in the computer is that the row 2 that we used to have has literally been changed to this new one. So that the row operations now are going to refer to this new row 2. So if we look at what we need to do, in row 1 at the moment we have got an element 2 and we want to get 0. So what we need to do is to take row 1, that's in the table above, and subtract from that 2 lots of row 2. That's the new row 2. If you do that, it is a simple subtraction. That becomes -1, 1/2, 0, 1, -1/2, 0, and a value of 10. So just trying to indicate what we've just done on the diagram with the arrows there. We've taken the row 1 in the top table and subtracted 2 times row 2 from the second table. Now looking at the third row, we can see that the element in the third row is equal to 3. So we're going to have to do a similar sort of thing with this row. So now we're going to do row 3 minus 3 lots of row 2. Again, it's the new row 2 that we're talking about here to produce a new row 3 in a second. And if you do that, you get negative 5 over 2, negative 1/4, 0, 0, negative 3/4, 1, and then a value of 1. Finally, moving to row 4, we can see that the element there is minus 6, so this time we'll need to do row 4 plus 6 row 2. And completing that gives you the values 2, negative 1/2, 0, 0, 3 over 2, 0, and 42. Well, we could look at interpreting the tableau as we've got it at the moment. Remember that the basic variables are, which are R, Z, and T. Those are the ones which are non-zero. So how do we read off their values? Those are read by looking along the table to the value. We've got currently R is equal to 10. Z is equal to 7. And T is equal to 1. The other values, X, Y, and S, are all going to be equal to 0. Well, we now repeat the whole procedure again, looking first of all for the negative values in the profit row. There's only one this time, which is in the column for Y. And we then, so working out the theta values, we take that column for Y and divide the value by the number that we find there. So the theta values, the first one is 10 divided by 1/2, 20. The second one, 7 divided by 1/4, 28. And the third one, 1 divided by negative 1/4, negative 4. Now remember that the theta values have to be positive, or at least they don't have to be positive, but we want the smallest positive value. That's like imagining back to that graph, moving through the graph within the feasible region. If we went negative, we would move out in the wrong direction. We want to move as far as the next point, so we want the smallest value, which is at 20. So that defines then the pivot, which is this time the element in the first row and column Y. That's the pivot. That means that Y is the entering variable and R is going to exit, so that now our basic variables are Y, Z, and T. We want to make that pivot column 1, 0, 0, 0. And we do that then by a series of row operations. The first one is to take what is now row 1, because these are all renumbered, row 1, row 2, row 3, and row 4. So we take the row 1 and divide it by the value in row 1, which is 1/2. And that gives -2, 1, 0, 2, -1, 0, and 20. Well, that gives us a new row 1, which we're going to use for the row operation. So looking at row 2 in the table above, we see that the value there is a quarter, so we need to take row 2 minus 1/4 of row 1, and again this is the new row 1. And doing that, you get the values 1, 0, 1, negative 1/2, 1/2, 0, and a value of 2. In row 3, we can see that the value is negative, the number is negative 1/4 at the moment, so we're going to take row 3 and add 1/4 of row 1. And that gives us negative 3, 0, 0, 1/2, negative 1, 1, and 6. Finally, in row 4, at the moment we have a value of negative 1/2, so if we take row 4 plus 1/2 of row 1, then we get the values of 1, 0, 0, 1, 1, 0, and 52. If there were negative values in the profit row, we'd have to do the whole thing through again. However, now you can see that they're all positive, or at least greater than or equal to 0. And so that means we've found our optimal solution. We can read off then from the tableau what we have. We've maximized the value of P, and that's now equal to 52. The basic variables we can read off, the value of Y is equal to 20, Z is equal to 2, and T is equal to 6. The other variables, X, R, and S, are all equal to 0. So it means that our profit, 52, is given by 20y plus 2z. So that would be the solution in terms of how many, whatever the question was about, x, y, and z, whatever they were in the question, that would be how many of each you were buying. The mark allocation for this sort of question is quite complex. In fact, the first M1 is scored by identifying the first pivot, and then an A1 for then correctly getting the new row 2, so in here. Following that, in the first run through the tableau, there is a method mark M1 and A1 for getting one of the rows correct, and then a second A1, but it's the correct answer only. In other words, you need to get the full tableau correct to score that second one. The A1, the top here, also, as well as doing the division by 4, you must also have correctly got the basic variables changing. The second run through the tableau is marked in a similar way for an M1, A1, and A1. This time only the 3 marks, and you don't necessarily need to, sorry, I beg your pardon, 4 marks, M1, A1, and then another M1, A1. You don't get penalized twice if you haven't got the basic variable correct, but again, the basic variable should have changed at this stage. There are then method and A marks for getting the correct variables, the values of the variables, so M1 and A1. for at least 4 of those correct, and a final A1 if it was all correct, so a correct answer only. Well, that's the end of this lecture about the Simplex Tableau. Other modules and units can be found on the website, which is www.furthermaths.org.uk.